In this video, we're going to be proving a little combinatorial identity. So it says that if n is a positive integer greater than 1 and m is a non-negative integer that's less than n, then if we add up -1 to the k times k to the m times n choose k, we'll get 0. So you can think of m as varying from 0 up to n minus 1. So no matter what power we pick in these terms, we'll get 0 as long as m is less than n. It turns out that when m is equal to n, you'll get something non-zero, but we won't concern ourselves with that. So first, let me write down the one-line proof, and then I'll explain how this is actually a proof. So this is the identity we're trying to prove, and the identity that we're going to use to prove it is this one. Okay, so it says that if I replace this k to the m by e to the kx, x is just some dummy variable, I get 1 minus e to the x all to the nth power. So let's think about why that's true. Well, this is e to the x to the kth power. So this is minus e to the x to the kth power here. And now I'm multiplying by n choose k. So this is exactly the binomial theorem where I'm applying it to 1 minus e to the x. So this identity is pretty straightforward. Now, how does this prove the identity I want? Well, if I think about expanding e to the kx as a power series, the terms will be powers of kx divided by some factorials. So the mth term, the coefficient of x to the m, will be exactly this thing, but divided by m factorial. So basically, we want to show that the coefficients of x to the m, as long as m is less than n, will be 0. So if we look over here, 1 minus e to the x, well, e to the x starts with a 1. So when I subtract it from 1, I'm going to get something that starts with negative x and then minus, well, whatever, all to the nth power. So the lowest order term that's non-zero here is x to the n. So if I look at any lower power, it's going to be 0. So all the powers here that are below x to the n drop out, and those are exactly these sums that I'm looking for, except with this factor of 1 over m factorial. Or equivalently, you could think about differentiating this m times. Each time you'll get another factor of k. So as long as you differentiate it less than n times, you'll get something that's 0 because of the powers of x over here. Now there's another, you could say, one-line proof of this. So k to the m is a polynomial in k. So what I'm basically doing is taking some values of some polynomial, here x to the m, and I'm subtracting repeatedly. So this is actually the nth forward difference of x to the m, and then I evaluate it. 0. Okay, so what that's saying is I take the polynomial x to the m, and I look at its first n values. So I've got 0 to the m, 1 to the m, 2 to the m, 2 to the m. Then I take the differences repeatedly. So I do 1 to the m minus 0 to the m, that's 1 to the m, 2 to the m minus 1 to the m, And now the nice thing about this is that each time I take a difference of a polynomial of degree m, the degree drops by 1. So in general, if I take the mth forward difference of x to the m, it's a lot like taking a derivative. I'll end up with just m factorial. So after doing this m times, I'll end up with a constant, but n is bigger than m. So I'm going to take the difference at least one more time. So eventually I'm going to get a bunch of copies of m factorial. The number of copies of m factorial will be n plus 1 minus m, but that detail isn't too important. I'm going to have at least 2 copies of m factorial. And then when I take the differences, wow, I'm taking differences of constants. So the nth difference of x to the m is going to be 0. It actually doesn't matter what x is here. I could plug in anything I want. So I could replace this k by, k plus 1 or k plus 7, so that as long as I have n plus 1 consecutive values of x to the m, I will get 0 in the end.